We want to look at this question related to properties of expectations. So we're told that there's a random variable x and we're given its expected value is 3 and its variance is 4. And you want to, number one, find expected value of 3x plus 2. Right? So we want to find this. Now here we're going to use the fact that expectation is a linear operator. Since expectation is a linear operator, now here the question arises, what do we mean by linear operator? Let's try to understand what we mean by this term. So linearity means that, what does linearity mean? Linearity means that expectation operator can go inside summations, means that expectation operator can go inside summations and constant multiples can come out. This is what you mean by linearity. And constant multiples can come out, right? Essentially, what we're saying is that, so when we say that expectation operator can go inside summations, what we mean is that the expectation of a sum is the sum of expectations, right? The expectation of a sum is the sum of expectations. So we can take it inside a sum is the sum of expectations. That's what we mean by this. Right, so say we had expected value of x plus y. Now expectation of a sum is the sum of expectations that can go inside the summation operator. So it's expected value of x plus expected value y. What does it mean constant multiples can come out? This means that if we had, say, expected value of ax, we can just write it as a expected value of x, so constant multiples can come outside of the expectation operator type. So here we're going to use the fact that expectation is a linear operator, which essentially means that it can go inside summations and constant multiples can come out. This means that I can write, since expectation is a linear operator, we can write expected value of 3x plus 2 as 3 expected value of x plus expected value of 2, right? Why we can write this? We know expectation can go inside summation, right? So this becomes expected value 3x plus expected value 2. And because the constant multiples can come outside, so we're just written expected value of 3x is 3 times expected value of x, right? Because this was essentially, what we've done it, this was essentially expected value of 3x, which we know is just equal to 3 times expected value of x because constant multiples can come out, right? So here we're using the fact that expectation is a linear operator. Now this can further be simplified as 3. We know expected value of x is 3, it's given to us, and we know expected value of any constant is equal to the constant. So expected value of 2 is just equal to 2, right? So this is because expected value of x is equal to 3 given, right? This is given to us, and this is because expected value of a constant is just equal to the constant itself, right? So in this way, we have found 11, right? So in this way, we have solved for expected value 3x plus 2 using the fact that expectation is a linear operator, which means that you can take it inside sums and constant multiples can come out. This is part A. Now let's look at part B. So let's just erase this. Now let's look at part B. Part B asks us to find expected value of x squared. Now whenever you want to find expected value of x squared, you need to recall something. So recall that when we find variance of x, we know we can calculate it as expected value of x squared minus expected value of x whole square. Right? Using this, we can relate. What we'll do is we can use this formula for variance. Using this, we can relate, right, expected value of x squared to the mean and variance. Right? So we'll use the definition of variance, relate expected value of x squared to the mean and variance. So what we can do is we can write expected value of x squared. If I make this the subject over here, then this becomes variance of x plus expected value of x whole square, right? So the fact that, so basically if we use the formula for variance, from this we can relate expected value of x squared to the variance and expected value of x, right? Now we're told the variance of x is 4. Since variance of x is 4, and expected value of x is 3. It's given to us in the question, like over here 3 and 4. That is 3 given. From here we can find expected value of x squared as 4 plus 3 square, and this is 13. Here the key point to remember is that expected value of x squared can be easily calculated if you know variance of x and expected value of x. If you know variance of x and expected value of x, right? So the key thing to remember here is that expected value of x squared can be easily calculated once you know variance and expected value of x, which we knew in this part. Because we can use the formula for variance to relate expected value of x squared to simply the variance and expected value of x. So just remember, whenever for any random variable, you want to find the expected value of its square. If you know its variance and you know its expected value, then you can just use the formula for variance to relate the expected value of the square of the random variable to its variance and expected value. Now part C is expected value of 2x plus 3 square. The first step that we're going to do is we will expand this, right? So that's the first thing that we're going to do is we're going to expand this, right? So we will first expand. And we'll see in a bit why it was important to expand. We'll just comment on that there in a bit. We'll first expand, we will first expand 2x plus 3 whole square using a plus b whole square. Right? We know, okay, a plus b whole square is just a square plus b square plus 2ab. So using this, we will expand this 2x plus 3 whole square, right? So we can write this as 2x plus 3 whole square. So this will become expected value of 4x squared plus 9 plus 2 2s are 4, 4 3s are 12x, right? So we just simplify this. This was essentially 2x squared, this was 3 squared, and this was 2 into 2x into 3, right? So we just applied a plus b whole square to expand this, right? Now, since expectation is a linear operator, and like we just discussed, what do we mean by linearity? Linearity means that expectation of a sum is sum of expectations, essentially, which means that it can go inside sums, and constant multiples can come out, right? So we can write expected value of 2x plus 3 whole square as 4, expected value of x square plus 9 plus expected value of 9 plus 12 expected value of x. Again, why can we write it like this? Because expectation is a linear operator, right? Which means that expectation is sum of expectations. We can write this as expected value of 4x square, right? This is essentially expected value of 4x squared. This is plus expected value of 9 plus expected value 12x, right? Because expectation can go inside sum, and because constant multiples can come out, we can just write this 4 outside here and 12 outside here, right? So we can basically write this statement based on the fact that expectation is a linear operator. So expectation can go inside sums and constant multiples can come out. Now we can write this further as 4 into 13 plus 9 plus 12 into 3. Now, where does this come from? This is expected value of x squared from part B that we just calculated using the variance of x and expected value of x from part B. And this comes from the fact that, like we discussed in part A, expected value of a constant is just that constant, right? This follows from there. And this follows that expected value of x is equal to 3 is given. So if we simplify this, this just turns out to be, right, so we can just calculate this as 4 into 13, 4 into 13 plus 9 plus 12 into 3. So it turns out to be 97. Sorry, this just turns out to be 97. Now, something to highlight over here was, we said that we have to first expand 2x plus 3 whole square. Why is that important? Let's just quickly look at that, right? We said we have to first expand, right? So let's just look at the warning here. We said now we have to first expand this using a plus b whole square, right? Why do we have to do that? This is because expected value of ax plus b square, right, is not equal to a expected value of x plus b whole square, right? Because the idea is that linearity, we said expectation is a linear operator. Linearity lets expectation go inside sums. So it can go inside sums, go inside sums and scalar multiples not non-linear functions like squares. Right, this is important, right? Linearity means that it can go inside sums, right? Which means it can go inside sums, which means that expected value, like we said, x plus y is just expected value of x plus expected value y. Expectation can go inside summation, right? Expectation of a sum is the sum of expectations. It can go inside scalar multiples, right? Constant multiples can come out, scalar or constant multiples, right? This is possible. But expectation cannot go inside non-linear functions like squares. You can't say okay, expectation can't go inside the square. Like this is not possible, right? Okay, you can write this like this. It cannot go inside the square. Right, so just keep in mind, linearity simply means that it can go inside sums. So expected value for sum is the sum of expectations. Constant multiples can come out, but expectation not cannot go inside any nonlinear function like square. So that's why in this case we had to first expand it. Expectation cannot directly go inside a square, right? So if x plus y square can't be that expectation is going inside a square. That's not possible. You have to first expand it, and then you can apply linearity where expectation can go inside the summation.